The Big Bang Theory proposes that the universe began as a singularity, a point of infinite density and temperature. At this incredibly compact state, all matter, energy, space, and time were concentrated into a single point. However, we currently lack a complete understanding of what triggered this singularity. Within this singularity, the laws of physics, as we understand them, break down. This means that our current understanding of the universe cannot fully explain what happened at the exact moment of the Big Bang. However, we can still explore the subsequent events that follow. As the universe expanded, it rapidly cooled down. Around 10 to the minus 36 seconds after the Big Bang, a process called cosmic inflation is believed to have occurred. Cosmic inflation suggests that the universe experienced an exponential expansion, increasing its size by an enormous factor in an extremely short amount of time. This expansion allowed the universe to become much larger and more homogeneous. During this period of inflation, quantum fluctuations, tiny fluctuations in the fabric of spacetime, may have played a significant role. These fluctuations are a fundamental aspect of quantum mechanics, and they can give rise to the formation of particles and energy. Some scientists propose that these quantum fluctuations acted as the seeds for the formation of galaxies and other cosmic structures we observe today. Around 10 to the minus 36 seconds after the Big Bang, the universe had cooled down sufficiently for fundamental particles to form. These particles included protons, neutrons, and electrons. As the universe continued to expand and cool, protons and neutrons combined to form the nuclei of simple atoms, such as hydrogen and helium. Over billions of years, gravity gradually pulled matter together, leading to the formation of stars, galaxies, and larger cosmic structures. This process of gravitational attraction allowed matter to clump together and form the complex universe we observe today. While the Big Bang Theory provides an elegant framework for understanding the universe's origins, it does not explain what caused the initial singularity or what triggered the rapid expansion. In religious and theological contexts, the concept of God is often associated with the creation of the universe. According to various religious beliefs, God is seen as the ultimate cause and initiator of all existence, including the Big Bang. It is important to note that these beliefs are based on faith, personal experiences, and interpretations of sacred texts, rather than empirical evidence or scientific observation. From a theological standpoint, the idea of God as the trigger for the Big Bang does not conflict with scientific understanding. Science aims to explain the natural processes and mechanisms behind the universe's development, while religious beliefs often focus on the philosophical and metaphysical aspects of existence. Religious texts, such as creation stories, describe God's role in bringing the universe into being. They depict God as the source of all existence, who initiated the creation through an act of divine will. However, it is important to recognize that these stories serve as symbolic narratives rather than literal scientific explanations. It is worth noting that science operates within a framework of natural explanations based on empirical evidence, while religious beliefs often encompass a broader range of concepts, including the supernatural and the transcendent. As a result, the question of what triggered the Big Bang falls outside the purview of scientific investigation and remains a matter of personal faith and philosophical contemplation. Ultimately, the perspective of God as the trigger for the Big Bang is deeply rooted in religious faith and the belief in a higher power. It offers a philosophical and metaphysical interpretation of the origins of the universe that complements, rather than conflicts with, scientific understanding. Science offers a different perspective on the origins of the Big Bang. According to scientific theories, the universe began as a singularity, an infinitesimally small and infinitely dense point where all matter and energy were concentrated. But what caused this singularity to expand? In the framework of scientific understanding, the precise cause of the singularity and the trigger for its expansion remain unknown. The laws of physics, as we currently understand them, break down at this incredibly high energy and high density state, preventing us from providing a definitive answer. However, scientists have proposed several hypotheses that shed light on the subsequent events. One hypothesis is cosmic inflation. It suggests that shortly after the initial singularity, the universe underwent a period of rapid expansion, growing exponentially in a fraction of a second. This expansion was driven by a hypothetical field called the inflaton field. The inflaton field temporarily dominated the energy density of the universe, causing it to expand at an extraordinary rate. During this inflationary period, the universe underwent a remarkable transformation. It smoothed out irregularities, making it more homogeneous and isotropic on large scales. It also provided the conditions for the formation of galaxies, stars, and other cosmic structures that we observe today. Another hypothesis focuses on quantum fluctuations. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, allows for the spontaneous creation of particles and energy fluctuations in empty space. These fluctuations could have influenced the expansion of the universe, serving as the seeds for the formation of structures in the early universe. As the universe expanded and cooled down, the immense energy transformed into matter. According to Einstein's famous equation, E equals mc squared, energy and mass are interchangeable. As the universe continued to expand, protons, neutrons, and electrons formed, eventually leading to the creation of atoms and the beginning of the cosmic evolution we observe today. It's important to note that while these scientific explanations provide plausible models for the early universe, they are still subject to ongoing research and refinement. Scientists continue to explore the nature of the singularity, the potential causes of inflation, and the precise mechanisms behind the formation of particles and structures. One scientific hypothesis proposes that a process called cosmic inflation triggered the expansion of the universe. Inflation suggests that the universe experienced a rapid and exponential expansion in a fraction of a second. This expansion might have been fueled by quantum fluctuations, which are tiny fluctuations in the fabric of spacetime. Cosmic inflation is a theoretical framework that suggests the universe underwent an extraordinary expansion shortly after the Big Bang. This rapid expansion occurred at an incredibly high rate, causing the universe to grow exponentially. The inflationary period is believed to have lasted for a minuscule fraction of a second, but had a profound impact on the structure of the universe. During cosmic inflation, a hypothetical field called the inflaton field dominated the energy density of the universe. The inflaton field possessed unique properties that caused spacetime itself to expand rapidly. As the universe expanded, it carried along with it the matter and energy within it, stretching the fabric of space itself. This inflationary expansion had several significant effects on the universe. First, it smoothed out irregularities and inhomogeneities, making the distribution of matter and energy more uniform on large scales. This accounts for the observed isotropy and homogeneity of the universe. In other words, it explains why the universe appears similar in all directions. Second, inflation provides an elegant explanation for the origin of the large-scale structure we observe today, such as galaxies and clusters of galaxies. Tiny quantum fluctuations in the early universe, caused by the inherent uncertainty of quantum mechanics, were stretched to much larger scales during inflation. These fluctuations served as the seeds for the formation of cosmic structures. Quantum fluctuations are an inherent aspect of quantum mechanics, the branch of physics that describes the behavior of particles at the smallest scales. According to quantum theory, empty space is not truly empty but filled with virtual particles popping in and out of existence. These fluctuations can create temporary imbalances in the distribution of energy and matter. During inflation, these quantum fluctuations became stretched across vast distances, becoming the initial density fluctuations that eventually led to the formation of galaxies and other cosmic structures. These fluctuations acted as seeds for gravitational collapse, where regions of slightly higher density attracted more matter through the force of gravity, forming structures over billions of years. While the concept of inflation and the role of quantum fluctuations offer compelling explanations for the structure and properties of our universe, it is essential to emphasize that these ideas are still subject to ongoing scientific investigation and refinement. Another scientific explanation for the origins of the universe revolves around energy conversion and particle creation. As the universe expanded, vast amounts of energy were converted into matter. This process is rooted in Einstein's famous equation, E equals mc squared, which describes the equivalence of energy and mass. According to Einstein's theory of relativity, energy, E, and mass, m, are two different manifestations of the same underlying phenomenon. They are interchangeable through the equation E equals mc squared, where c represents the speed of light in a vacuum. This equation implies that a certain amount of energy can be converted into an equivalent amount of mass and vice versa. In the early moments of the universe, as it continued to expand and cool down, the intense energy present began to transform into matter. This energy conversion process involved the creation of elementary particles, such as protons, neutrons, and electrons. As the universe expanded, it also cooled down. This cooling process allowed the energy to condense into particles. In the early stages, the universe was extremely hot and energetic, with temperatures far exceeding what we encounter today. In these extreme conditions, the energy was in the form of high-energy photons and other particles. As the universe expanded and cooled further, the energy of these high-energy photons began to decrease. This decrease in energy allowed the conversion of energy into matter, resulting in the creation of particles. The most abundant particles formed during this period were protons, neutrons, and electrons, which are the building blocks of atoms. Protons and neutrons, known as nucleons, are the constituents of atomic nuclei. Electrons, on the other hand, are negatively charged particles that orbit around atomic nuclei. Through the electromagnetic force, protons and electrons are attracted to each other, forming stable atoms. Through the process of energy conversion and particle creation, the universe transitioned from an era dominated by energy to one where matter began to take shape. This transformation laid the foundation for the development of more complex structures, such as galaxies, stars, and planets, as gravity pulled matter together. It's important to note that the energy-matter conversion process is a fundamental aspect of the early universe's evolution. It is a consequence of the physical laws and interactions between particles during the expansion and cooling of the universe. Let's consider the fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. These forces played crucial roles in shaping the universe. While science does not provide a definitive answer to what triggered the Big Bang, it helps us understand the physical processes that occurred during and after this event. Gravity is the force that governs the interactions between massive objects. It is responsible for the attraction between objects with mass, such as planets, stars, and galaxies. In the context of the Big Bang, gravity played a significant role in the subsequent evolution of the universe. As the universe expanded after the Big Bang, the force of gravity acted as a binding agent, pulling matter together and leading to the formation of structures. Over billions of years, the gravitational attraction between matter caused the clumping and clustering of galaxies, the formation of stars within galaxies, and the aggregation of matter into cosmic filaments and voids. Electromagnetism, on the other hand, is responsible for the interactions between charged particles. It includes the forces of attraction and repulsion between electrically charged particles. Electromagnetic forces played a vital role in the formation and stability of atoms, molecules, and the intricate structures we observe in the universe. During the early stages of the universe, when it was extremely hot and energetic, the electromagnetic force was unified with the weak nuclear force, forming the electroweak force. As the universe cooled down, these two forces separated, leading to the distinct electromagnetic and weak nuclear forces we observe today. The strong nuclear force is responsible for binding protons and neutrons together within atomic nuclei. This force is incredibly strong but acts over very short distances. It ensures the stability of atomic nuclei and plays a central role in the energy production of stars through nuclear fusion. The weak nuclear force is responsible for certain types of radioactive decay and interactions between elementary particles. It plays a crucial role in processes such as the fusion of hydrogen in stars, the decay of radioactive isotopes, and some reactions in particle accelerators. These fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, interact and shape the universe as we know it. They govern the behavior of matter and energy, leading to the formation of structures, the evolution of stars, and the intricate processes that shape our cosmic environment. While science does not provide a definitive answer to what triggered the Big Bang, it offers valuable insights into the physical processes that occurred during and after this event. By understanding the role of these fundamental forces, scientists can explore the dynamics and behavior of the universe as it evolved from its early stages to the present day. So, what triggered the Big Bang? While science offers various hypotheses and theories, it does not provide a concrete answer. Some find solace in the idea of a divine force, while others delve into scientific explanations rooted in cosmic inflation, quantum fluctuations, energy conversion, and the fundamental forces of nature. Ultimately, the question of what triggered the Big Bang remains a captivating mystery, driving our curiosity to explore the vast depths of our universe. Thank you for joining me on this cosmic journey. Don't forget to like, share, and subscribe for more mind-expanding content. Until next time, keep exploring and questioning the wonders of the universe.